All right. This is about the binomial theorem. A binomial is two terms, A plus B. Two terms, two named binomial. And we want to know its powers. It's zeroth power, first, second, third, fourth, and so on. We have first power of A plus B is 1. This is identical. A plus B to the first is 1A plus 1B, all very obvious. Now, the square of A plus B, if you expand it out, is A squared plus 2AB plus 1B squared. If you multiply that by A plus B again, you get A plus B cubed, and this expands out to 1A cubed plus 3A squared B plus 3AB squared plus 1B cubed. Fourth power, if you multiply this out, is 1A fourth plus 4A squared cubed B plus 6A squared B squared plus 6AB cubed plus 1B to the fourth. Now here's the funny part about it. If you look at each of these terms, each coefficient equals the sum of the two above it. 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 1 equals 3. Well, imagine these are zero coefficients out here. So 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1 plus 0 is 1. And so on. And that should be obvious because if you get this one here, the third term, the power of 3, what you do is you take the square and multiply it by A plus B. That'll have the effect of shifting this over 1 for the A and the other direction for the B, and you add them up, and so adjacent terms add for the coefficients. Now, so these coefficients, they form Pascal's triangle. You add each term for each of these, you add the sum of the two entries above it. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and so on indefinitely down forever. All right. We call these terms the binomial coefficient, starting from R. Pronounced NR. Sometimes pronounced N choose R, because it has to do with something called combinations, number of ways to choose R things from N. So N choose 0 and N choose N is 1. That means all these ones here and all these ones here. N choose 1 equals N choose N minus 1 is N. Therefore 1, 2, 3, 4, 5. Therefore 1, 2, 3, 4, 5. All right. Now, so that defines these. This row and this diagonal, this diagonal, this diagonal, but these diagonals, it's not as obvious. So here's what we do. Turns out, you can have a formula for it. It depends upon something called factorials. A factorial written N exclamation mark. N factorial is this. 0 factorial is 1, and N factorial is all the integers from 1 up to N multiplied together. So all the integers less than or equal to N as factors, therefore the name. It also equals a number of ways to arrange N things in a line. If you have N things and there's N choices for the first thing, N minus 1 for the second thing, N minus 2 for the third thing, and so on down the line until the last thing is just one choice. If you expand, if you have a scientific calculator, you probably can access N factorial in the probability section, and various factorials. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1 is 2, 3 factorial is 6, 4 factorial is 4 times 3 times 2 times 1 is 24, 5 factorial is 5 times bigger, 120, 6 factorial is 6 times bigger, 720, and so on. 10 factorial is about 3,628,800. 10 things in a row, it takes more than 3.6 million ways to arrange them in a line, and so on down the line. It goes very, very quickly, very, very fast. Therefore, the exclamation mark. Turns out that 70 factorial is too big for, at least my calculated. It's bigger than 10 to the 100th power. That's just 70 things. There's more ways to order 70 things than there are atoms in the visible universe. Okay, here's the formula. N choose R is N factorial over R times R N minus R factorial. All right, now let me get to that later. We give an example. 3 choose 1 times 4 choose 2. 3 factorial, 3 choose 1 is 3 factorial over 1 factorial times 2 factorial. 4 choose 2 is 4 factorial over 2 factorial times 2 factorial. Here we have 1 times 2 times 3 over 1 times 1 times 2. This is 4 times 3 times 2 times 1 over 2 times 1 times 2 times 1. And so usually things cancel out. The 2 times 1s cancel, yada, yada, yada. Get 18. All right, now let's just go back. That's these. Now, okay, there's a proof of the binomial theorem by mathematical induction, modified mathematical induction. We'll start from the edge of Pascal's triangle. Prove all these ones and all these ones. So here we go. N choose 0 equals n choose n equals 1. All right. And if we check it out, n factorial over 0 factorial times n minus 0 factorial, that's n factorial over 1 times n factorial is 1, as it should be. Now, if we try here, n factorial over n factorial times n minus n factorial, that's n factorial over n factorial times 1, also 1. So these equal these, and the initial step is confirmed. This works for the edge. Now, let's assume that the factorial works for k minus 1, n equal k minus 1, up to a certain depth in Pascal's triangle. Now we'll have to prove it for the next row. That's the question. All right, here's how it goes. So k choose r equals k minus 1 choose r minus 1 plus k minus 1 choose r. All right, so that's the recursion that defines the factorials. K choose r, okay, it's just a bunch of really messy calculations, and I'm going to skip that. You can review it more yourself. So things subtract and certain things. For the k minus 1 factorial, let's see now. Okay, whatever. This equals that because of factorial. And you do some arithmetic and it works. So the induction step is confirmed and the theorem is proved. So given, okay, hold on. So given the recursion formula for the binomial, that each entry is equal to the sum of the two others, then this formula for the binomial coefficients follows. Okay, now binomial theorem says that if you take an nth power of a binomial, a plus b, then you get this long sum. All those a to the n minus 1b, a to the n minus 2b squared, yada, 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 a to the n minus k, b to the k, all the way up to b to the n. And then each of these is multiplied by a binomial coefficient. N choose 0, n choose 1, n choose 2, yada, yada, n choose k, and n choose n. For example, x plus y to the 6th power. All right, 6 choose 0, x to the 6th times plus 6 choose 1, x to the 5th y, 6 choose 2, x squared y squared, 6 choose 3, x cubed y cubed, 6 choose 4, x squared y fourth, 6 choose 5, x y fifth, 6 choose 6, y to the 6th. And okay, I could calculate all these using the factorials, but in this case, it's easier just to do this constant sums. So okay, we got last time we got as far as 1, 5, 10, 10, 5, 1. Okay, so you have a 1, then 1 and 5 is 6, 5 and 10 is 15, 10 and 10 is 20, 10 and 5 is 15, 5 and 1 is 6, 1 and 0 is 1. So 1x to the 5th plus 6x to the 5th y plus 15x to the 4th y squared plus 20x cubed y cubed plus 15x squared y to the 4th plus 6xy to the 5th plus 1y to the 6th. So that shows up. Okay, we went through this. Here's an example. 5 choose 0 plus 5 choose 1 plus 5 choose 2 times 5 choose 2 plus 5 choose 4 times plus 5 choose 5. What does that equal? was the sum of all the binomial coefficients along a row of Pascal's triangle. Well, the theorem this is equal to 1 plus 1 to the 5th power, because 5 choose 0 times 1 to the 5th plus 5 choose 1 times 1 to the 4th times 1, 5 choose 2, 1 to the 3rd, 1 squared, yada, yada, yada. And in the end, okay, so this on the left side will be 1 plus 1 to the 5th power, or 2 to the 5th, or 32. So that's what this is. That's easy enough to check. If you add up all these, 1 plus 5 plus 10 plus 10 plus 5 plus 1, yes, that does indeed equal 32. Now let's try if it's alternating. 5 choose 0 minus 5 choose 1 plus 5 choose 2 minus 5 choose 3 plus 5 choose 4 minus 5 choose 5. This alternating between plus and minus and plus and minus and plus and minus and so on. That works if we're taking 1 plus negative 1 to the 5th power. But 1 minus 1 to the 5th power is 0 to the 5th is 0. These all cancel out. And again, it makes sense. 1 minus 5 plus 10 minus 10 plus 5 minus 1. Every term cancels. There's that.